everybody.
Thanks.
I'm Per.
Yeah, I'm Carina. Thanks for inviting us. Thanks for coming. We are both founders of Speedment, and we are also fighting with Java every day. We're not only Java fighters, we are also karate fighters.
And I think with that piece of information you can derive the chain of events that led up to this unfortunate event. You should see the other guy.
This was not the look before. So today we're going to talk about the need for speed. So let's start. This is kind of the opposite of speed. You have seen this, I'm sure. So actually what the brain does to you is, if something is 100 milliseconds, then you think it's direct response. If it's 1 second, you actually can experience a delay. 3 seconds, you start to become frustrated, and actually they know that 57% leave the site. And 10 seconds, then your brain completely stops. You start to think of something else. But don't take my word for it, I will try it on you. So let's start with 100 milliseconds. Are you ready? Clicking. Quick, wasn't it? We will do 1 second. It was pretty, you could see it, but still it was acceptable. Now 3 seconds. This long. And now 10 seconds. Start now.
Raise your hand when you start to think about something else. This is, yeah, that's an honest guy.
You were kind of cheating because now you were talking. So, this is actually good to see because you can experience how frustrating it is. But of course it's not only your brain that thinks this is frustrating. If you go to page views, Google said that they lost 20% of the traffic, only a half-second delay. Amazon said that they lost 1% of sales for every 100 milliseconds delay. And also for a company it means that they invest in unnecessary hardware and license cost, and it also destroys the brand. If someone needs to wait, for instance, for a paying transaction, it takes too long, they start to feel that I can't trust this company. So that's why delays are important. And I will jump down on my one leg and...
Okay, leave it to me.
Yeah.
Okay, easy to say. Okay, thank you. Yeah, this is a picture showing the sun and some of our planets. Good. And this tiny little piece here, this blue planet, that's the Earth, that's what we call home. And it's 1.3 million times smaller in volume than the sun. And Carina was talking about 200 milliseconds, and I'm going to talk about 200 nanoseconds, which incidentally is 1 million times faster than 200 milliseconds. Because we humans, we live in the middle world. We understand things that are average size and average time. We see like objects like this, but we don't see atoms or protons or electrons. So that's why I have this analogy. We're going to go from 200 milliseconds to 200 nanoseconds. And I'm going to explain why. So why does speed matter? Of course, now that we are in New York, of course, fintech and high-frequency trades, speed is important. Input the value of information rapidly decays as times go by. In AI, it's good to have something that's, because you can calculate things instead of your neural network. You can train your neural network much faster and you get better predictivity. In IoT, you can look at more parameters and maybe predict when something is about to break or something like that. In logistics, you can look at more parameters and have a more optimal stock. In science and space, it's obvious why this is important, and especially in microservices architecture, when delays are added, speed is very important because you have a chain of 5 microservices doing something, And of course, everything is the sum of all the microservices, and they all add up. But it's not only about latency. It's about deterministic behavior. It's good if it's fast, but if it occasionally is slow, that's not good. And that's something we Java developers recognize a lot, because we all see garbage collection. What happened? Our application stops for 20 seconds. It used to be so fast, but something happened. Not so good. We want a low memory footprint. We want to have a low CPU utilization. We want to preserve our resources. We don't want to create so much object. We have to have a low memory pressure to maintain our caches in the CPU. We like parallelism. We like to be able to scale out. And all these things is something I want to talk about today. Okay, this is reality. Contrary to some politicians, the world is complicated. Usually you don't calculate just one thing and then you're ready. It's more like you calculate a lot of stuff and they all make up an aggregated result. So you start with something and then you end up with something a million times steps after that. And that's why it's so important that each step is so quick. So if you want to joke with words, if you break it down, it all adds up. So if you have total latency, and if you have a serial chain of events, the total latency will of course be the sum of the latencies that makes up that chain. And maybe you have millions of steps, and you want to do something in less than 1 second, so that's why I set up the ambitious target of 200 nanoseconds. I want to complete things in 200 nanoseconds.
Could you turn up your microphone?
Okay, I can, we have some technician here.
Yeah.
Is it better? Yeah, I think so. Okay, sorry. So, okay. So, I'm going to talk about different ways of doing this. First of all, I'm going to talk about clusters of nodes, because that's a very popular thing of way of solving problems. So, in one extreme, we can set up nodes on different sides of the country.
Turn that on.
It is on. Maybe I can move it closer to my mouth. Hello? Okay. So, we have some physical limitations here. It turns out that the speed of light will say that it takes 15 milliseconds to go from San Francisco, where I live, to New York, if it's just light in the air. But it's usually fiber, so it's even slower. So 45 milliseconds is the fastest you can do a round trip result, even though your computational power is indefinite. And we were talking about 200 nanoseconds, so this is several orders of magnitude too slow. So let's have another shot at the problem. Let's say that we have 2 Linux hosts, put them together, make some duct tape around it, and connect them directly via 10 gigabit Ethernet. What is the latency there? Yeah, with some tweaks you can get down to 40 microseconds. If you resort to busy polling and put your processes tie down to a certain CPU, you can go down to 30 microseconds. And if you are an expert and do some good black belt technology, you can come down to 25 milliseconds. That's 100 times too slow. Doesn't work. And of course, if you have routers and switches, it will introduce an additional delay, especially if you run them in the cloud, because they have something called software networks, and that will introduce additional delays. So this is not really the way to go. So what about having different processes on the same machine? Well, that is better, but again, you see, inter-process communication is in the milliseconds, and you have to switch, you do a context switch, you will ruin your caches, and your TLB will be affected by this process switch. So it's not really good enough. It's 10 times too slow. So that leaves us with the JVM itself. What can we do within the JVM? Well, if we read just the memory position, it's 100 milliseconds. And if we have a volatile read, it's about the same. If we can hit the L3 cache, it's 20 nanoseconds. We can go down, and we can even hit 0.5 nanoseconds if we can remain in the L1 cache. And of course, it's a narrow definition what the delay is for CPU listed. Some say it's 0 by definition, but it's very quick. So we need to be here somewhere. to be able to do something in 200 nanoseconds. So I will take a step back and look at an exemplary microservice architecture where we have different microservice services that does things. For example, up here we have some order management, and here we have different shards that shares on some keys. A to D here, E to L, M to T to Z here. And in order to understand how we should deploy this in an efficient and fast way on an architecture, we need to understand how the CPU looks like. This is a standard multi-core Intel CPU. And at the edges, the actual logic is, and the more to the middle, the more to the cache layer you see. So this is like L0, L1 and L2, and these are L3 caches in the middle. And they're actually shared between the CPU cores. So why not do like this? Each microservice will pin down to its own CPU and use the L3 as a communication bus. This will give you a very good performance. And you can do stuff in the nanoseconds. Wow. So, and of course, if you have more CPU or CPUs on the same physical die, you have to understand that it's called NUMA radios. So actually each CPU is a computer in itself connected with high-speed buses. So this is things you have to understand. So we have to invite this guy on the silicon. So that's end of part 1. Now come to part 2, which is the API we're using to access data. And that's standard Java streams. How many of you run Java 8 or Java 9? Most of you. Not everybody. But yeah, okay. I hope you will get there soon. So if you compare SQL and stream operation, there is a remarkable resemblance between them. This is of course no coincidence. For example, if you look at where corresponds to filter, and offset is skip, and count is it actually counts. It's very easy. But it's not only the operations you can do, but it's also something else. I wrote an article about this in Oracle Java magazine this summer. And in this article, I spoke about how to render Java streams to SQL. In this talk, I'm going to render them to something that traverses an in-memory structure instead, which is much faster. But they both share something called a declarative construct. This means that if you look at the upper portion, okay?
Make you comfortable.
Better or worse? Better. Okay. They share a declarative construct, meaning that if we tell the database to select all fields where the rating is PG13, we don't dictate how the database should do it. We only say that we want only those rows satisfying the predicate rating equals to PG13. The database might opt to do a complete exhaustive search, or it might use an index. Hopefully it will do an index search. But actually it's the same with streams. So we say that we want a stream, and then we say that that stream should only contain fields that has a rating equal to PG13. It doesn't say that it should produce each and every element and then evaluate the predicate. That is very, very important to understand, because the stream implementation, the stream is just an interface. The implementation can elect to use an in-memory index, for example, and only present those elements that fulfills this or some other requirement. So that is Speedment. Speedment is 2 parts. It's a Java stream ORM tool, which is open source, and which you can read on in the JavaOne magazine. And it's also an in-JVM memory acceleration. It's using exactly the same API, which is the stream, and can render that to an in-memory representation. And by that gaining orders of magnitudes, low latencies. So if you position Speedment, it's kind of in the left-hand corner. It's in the terabytes, the data you can use, but it's in the nanoseconds. Other solutions, like those with elephants and similar, can handle a lot more, but are significantly slower. So that's kind of where we are. So I'm going to show you a demo, and hopefully it will work, because last time I was here, my computer crashed and I switched application. So let's hope for the best. Very small. Okay, so I have here a JMH application, and I'm showing you two different streams. Can you see this? Fairly good. Okay. So there's first a simple stream, which is the stream over all fields. This is a Carina database, which is a publicly available database with fields and actors and stuff like that. And we want a stream that filters out each and every field that is a PG13, and we want to count that. That's a very simple stream operation, but it's still an operation. And then we have a more complex operation, which is we take all the fields, we stream them, we sort them in length, descending order. We skip the first 745, limit to 5, extract the get rental duration, and we perform some kind of system statistics on that. I'm sure those of you who have been working in streams will be very familiar with this. For those who haven't seen stream, this is a kind of a standard way of handling data. So let's see how fast that is. So I'm going to start. Benchmark. And while I'm starting, I'm going to explain the thing here, because it turns out it is so fast that I can't really measure it, because the time resolution on my Mac computer isn't enough. So I'm doing a little trick here. Instead of measuring delays, I'm measuring the throughput for a single thread, and then I invert that value. If I would have run this on a Linux machine, the time resolution would be enough, but not on a MacBook. So it's running here. So this is kind of a cliffhanger. This is a simulation. And there the result is, but it's so small that you can't really read it. Okay. We start with the complex one. We can do 400,000 operations with that complex stream on a laptop, on a single thread. I think that's impressive. And if we go down to the simple one, we can do like 6 million. If it would have been 5 million, it would have been 200 nanoseconds, but now it's actually faster than 200 nanoseconds. And the cool thing is that this can also run concurrently. So let me because the in-memory representation is immutable, and thus it's thread safe. So it scales very well with the number of CPUs that we have. And there something happened. Yeah, so it's lucky that I saved the results on a file. So the first one is involved with one thread, and the second one here is with all the threads. I have 4 CPUs on my MacBook Pro. So in this case, I was able to do almost 20 million streams on my laptop. And you can imagine how many you can do on your Xeon server-grade computer. So the performance is quite good. Okay, let's go back to the presentation. That's not the presentation. It's confusing. Okay. So, the solution is based on in-JVM memory streams. It's using Stream API. And the streams, they introspect their own pipelines, so they're able to optimize themselves regarding its own, and will be able to regard its own pipeline and terminate the operation. We use off-heap storage and indexing, so you can build up as big model as your RAM allows, like terabytes of data. We have immutable snapshots, so you can create new versions of your data by new snapshots, and all the operations are either order 1 or order log n, which means that it scales very well with the size of the data. It's not only the data that's off-heap, the collectors and aggregators that we have are also off-heap, and that's important if you have an application that runs for a longer period, and you don't only want to have your data garbage collection free, but also your actual application. So I think that is a very important thing. And it's taking care of something called escape analysis, which can, if you write your application cleverly, you can allocate your objects on the stack rather than on the heap. So let me just show a simple example. If we have a field, filter out everything that is rating pre 13, and we collect them to a JSON, and this is an off-heap aggregator in this case, then the application can see that, well, we have an index for rating, so it can immediately jump to the one that's only PT13, and it can jump like this in memory and just produce the output and copy that to off-heap memory in a very efficient way. And then we just iterate over each and every entity. So we never have to materialize the Java entity. They never exist. They only exist as a conceptual view of your data. And of course, you can map this to memory, so if you have a microservice architecture and you want to start a new microservice, you can use a map file to start it immediately. You can use sharding, where you have different keys. And this is an example of an existing in-memory solution. And I'm afraid that our competitors got the 10-second penalty that Carina talked about. So you can use your computer resources very efficiently. You can have much less RAM, you can use much less CPU, and you can have a much more predictable performance of your application. Less cost and happier users. Okay, I will just make another reference to astronomy. I like astronomy, so, and that's a hint, because how much is 1 second? How far would the light go in 1 second? Anyone? You're supposed to say the moon. Okay. So this is a difference between getting data from a database, if it takes 1 second, or getting it from the L1 cache, which is about 4 inches or 10 centimeters, so if you're on a metric system. And I think that illustrates the difference in performance. So conclusion, don't place your data on the moon, keep it there instead. And of course you can use any data, you can use any database, or you can use arrow files. So there's even a guy who did a connection to Google Docs Sheets, so you can pull in data from Google Docs. You can deploy it using Docker, Kubernetes, or on-prem, or whatever. And people have deployed this on Raspberry Pi. So it's a very wide range of target platforms. You can use any integration tool because it's just Java beans and Java library. And you can deploy it in like a Spring or any Java EE server container. The API is simple, you don't have to learn anything, it's standard Java 8. There are REST API plugins that you can use, you don't have to write your REST plugins. It's already compatible with Palo, which it's used to create frontends, and it's also ready for Java. And this is just an example of a fintech application we wrote, where we were able to reduce latencies from like 3 or 4 seconds to milliseconds, and it's much more rapid. You can write things. If you have just one thing that is slow, you can use Speedment for that and leave everything as it is. So you don't have to change everything. You can just change small parts. And you can try it out. You can download it today. Try it. There's a free trial license. And it's an initializer so that your entire product with bombs and everything. So, thank you very much. Any questions?
Do you have this presentation on your website?
We will get a copy of the presentation.
Yeah, I will send it to you, Frank.
Okay.
You can make it available.
Okay.
Yeah.
You mentioned the databases and you also mentioned Avro.
Yeah.
So does that mean that it can work with a Hadoop database that has Avro files?
Yes. If it has error files, you can work with it.
But not Per-Ake?
Not out of the box, but you can very easily write something called a stream source that can adapt to anything like that guy who wrote a Google Doc. Just implemented one method that can read a record from something.
Right.
So it's very easy to adapt it to a binary file or some other file format.
Okay.
Yeah. Okay. Thanks.
Sure.